Hello everyone. Today we will be solving question number 35 which was asked in the GATE 2022 set 1. So this question is from the heat transfer. So this question is from the heat transfer and is basically from the topic the Stephen Boltzmann law and or the Kirchhoff's law, right? So it comes under the radiation section. So as we know that heat transfer consists of conduction, convection and the radiation. So before directly going on to the question, let me just give you the brief concepts, or let me just remind you concepts regarding the uh, Kirchhoff law or the Stephen Boltzmann law. So as we know that Kirchhoff's law you might be heard of in the basic electrical thing, right? So but this is a little bit different from that. So it states that the total hemispherical emissivity of a surface at temperature T is equal to the absorptivity for the radiation coming from a black body at the same temperature. That is, this is the emissivity from a surface which is equal to the absorptivity of a surface at the same temperature, right? Where this alpha is the absorptivity, right? And absorptivity is also the ratio of the incident radiation to the absorbed radiation, sorry, absorbed radiation to the incident radiation, right? So let me just write it as radiation absorbed to the radiation incident, right? And there is another law which is Stephen Boltzmann law, and which is a very famous law, and it states that the maximum radiation energy emitted from a surface per unit time and per unit surface area is expressed as emissivity of a surface to this Boltzmann constant, right, to the fourth power of temperature, where this is the emissivity of a surface, T be the temperature, sigma be the Stephen Boltzmann constant, right, and whose value is 5.66 into 10 raised to power minus 8 watt per meter square per Kelvin 4, right, and T is the absolute temperature. Now coming over to the question, what we have been given, a flat plate, okay, made of cast iron is exposed to a solar flux of 600 watt per meter square at an ambient temperature of 25 degrees Celsius, and assume that the entire solar flux is absorbed by the plate. Okay, so this whatever solar flux it is getting absorbed by this plate, right, cast iron plate. Now cast iron has the lower temperature emissivity of 0.21 and Stephen Boltzmann constant, as we have just now read, and neglect all other modes of the heat transfer except radiation. Only radiation we have to consider, and using the conditions we have to calculate the radiation equilibrium temperature of the plate, and we have to calculate it in terms of the degree Celsius, right? So let us first of all draw diagram. Okay, let me just move to the next page. We draw that diagram. This is the plate, right? This is the surface. Ambient temperature is 25 degrees Celsius. This solar flux is coming 600 watt per meter square. Q radiation. Right, so this is a solar plate. If we write the given, we have G, which is the solar flux, is equal to 600 watt per meter square, sigma 5.66 into 10 to the power minus 8 watt per meter square Kelvin for TAVD 25 degrees Celsius, which is 298 Kelvin. If Ts we don't know, surface temperature, and alpha absorptivity has been given. Right now, since it has been given that the entire solar flux, whatever this radiation is coming over this plate, it is getting absorbed by the plate, right? And as per the Kirchhoff's law, what does it states that heat absorbed by plate would be equal to net heat transfer between plate and ambient. Right, so that means emissivity, absorptivity is equal to emissivity, right? And if we apply the Stephen Boltzmann law, right, and since the radiation flux is equal to S means solar flux, right, would be sigma Ts4 minus Ta4, because two temperatures have been given, and on substituting the values it would become 0.21 into 5.669 into 10 to the power minus 8 Ts4 minus O. And if we solve it, Ts would become 491 Kelvin, right? But we have to solve the temperature in terms of the Kelvin, so we will subtract minus 273 from here, and it would give us 218 degree Celsius, which is the right answer, right, for the radiation equilibrium conditions. Thank you.